So it is a pleasure to be here this morning and to share my research with all of you. The research that I'm going to show this morning is can be found in this paper, and I would like also to thank all the co-author and the people that helped me to write it up. So since my talk starts with this definition, this fractal dimension story, I cannot avoid to introduce what fractal dimension means. So, and if you have the time to go through this definition, and if this definition doesn't make sense to you at all, do not worry, because I spent more or less 3 months before sorting it out. So the nice thing that I'm going to do is instead to explain how I sorting out this kind of definition with some example that make more easy to understand what fractal dimension means. So for that, we start with segment. So if we have segment A, that for example, we hypothesize that have a dimension equal to is length 2, and we want to understand which is the length of the segment B through a scalar factor k, we can multiply our segment A by the scale factor. So if the scale factor is 0.5, of course, the results of the length of the segment B is equal to 1. So we can move also in 2D, and for example, for this triangle, if we multiply the base of the triangle and the height of the triangle by the scale factor k, that is always 0.5, we can see how big, or we can calculate the area of the small triangles. And as always, we have, if we just do some algebra over here, so that there is this rule that the area of the triangle B is equal to the sides of the big triangle A by k squared. And to make the long story short, in the 3D case, we just make this multiplication by the scale factor, and we have that our B volume is equal to A multiplied by the scale factor cubed. So there is this nice relationship between dimension and the k factor, the exponent of the k factor. So 1, 1. For 2D, we have k factor squared, and for 3D, we have a k factor cubed. So now, if there is this relationship, now I'm asking if we are going to measure the area of the triangle A without the area of triangle 4, this in the middle, and we probably still are able to measure through the Euclidean geometry. But if I'm going to iterate for infinite times this subtraction all in the middle of the triangle 1, the middle of the triangle 2 and 3, and so on, what we get is the so-known Sierpinski triangles. So if I'm going to ask now which is the dimension of the triangle B, so maybe we can guess that this triangle is something, can be 1 or 2, probably 2. But let's see sort out in which way we can find the dimension of this triangle. So through the k factor, we know that B is equal, as we saw before, A, so the sides of the triangle A by KD, in which D is the dimension of the triangle, but for now we leave as unknown. And A is 3 times B, because of course the triangle is 3 times the triangle of B. So if we do some algebra, we found in the end that 2 raised by D is equal to 3. So if we hypothesize that this triangle has a dimension equal to 1, we have that 2 is equal to 3. That of course is impossible. And if we assume that the dimension is 2, we have that 4 is equal to 3. Then this triangle, so the Sierpinski triangle, has neither a one dimension nor a two dimension. But if we move to the logarithms, we have that the dimension of this triangle is something like 1.585 and so on and so on. This is exactly what that means fractal dimension. Now, since we are working with data on the brain, so EEG and EEG data, Iguchi proposed an algorithm to estimate the fractal dimension directly on the time domain. So this is exactly what we need to estimate the fractality in the time series domain. So also here we have something that as a dimension go from 1 to 2. And what we have as upper bound and the lower bound is exactly this. So if we estimate the fractal dimension for a random noise from a time series based on the Gaussian noise, we have the estimation of fractal dimension equal to 2. That is more close to a very complex signal. Instead, if we have a time series like a ramp, the fractal dimension estimated by the Iguchi algorithm is equal to 1. So we have upper bound and lower bound. This means that everything is in between. All the time series that are in between these two upper and lower limits can be estimated with fractal dimension, and, for example, with this Weierstrass cosine has, for example, the fractal dimension equal to 1.5. So one thing that we have to keep in mind that some fractal dimension that is close to 2 have a signal that is really complex from the fractal dimension point of view, and something that is equal to 1 is very simple time series. Having all this knowledge and these tools, what we did in this experiment, we recruit 19 volunteers, and we perform a high-density EEG during a resting condition with open eyes, and we were able to extract 8 core resting state networks. That these resting state networks can be the default mode network, dorsal attention, auditory networks, language networks, ventral and dorsal attention, and a visual network. Now, instead of concentrating in the spatial point of view of this network, we start to understand in which way we can characterize the neuronal activity of all these networks. And one thing that we can do is, for example, move from the time to, because for each resting state network, so we can have one time series that characterize all the network. So we can move to the frequency domain, and we can have the power spectrum density divided by the main frequency band, so from delta to gamma, but also we calculate the fractal dimension. As you can see, especially for the gamma and the fractal dimension, seems that there is some order in the complexity or in the signal of these resting state networks. So to quantify this quantitatively, because thanks to the color, we can have a qualitative way to understand this diversification of the resting state network, we apply clusterization. In particular, we apply a hierarchical clusterization on the 5 bands frequency domain and on the fractal dimension. What we found, especially if we use the broadband, we cannot be able to diversificate the neuronal dynamics of these resting state networks. But instead, if we use the gamma feature, we were able to divide our 8 networks in 2 subgroups. One that is more like the default mode network, language network, so the high cognitive function, and the other part of the perceptual networks. The same thing can be done through the fractal dimension. As you can see on the dendrogram, we can have the high cognitive function as a cluster and the perceptual network as another cluster. We apply, just to be sure, one other complexity index, that is the entropy, but the entropy alone is not able to diversify across these 2 subgroups. At the level of the single subject, we performed this similarity index. And what we found is that the high cognitive functions are dominated by lower frequencies, so delta, theta, and alpha. Instead, the perceptual network are dominated by high frequency like beta and gamma. From the fractal dimension point of view, instead, we can have that the perceptual network has a more complex, from the fractal point of view, signal respect to the high cognitive function. We can use these results to test or compare, for example, a normal brain, healthy brain, with other pathological brain, and understand if this equilibrium is distorted through the pathology. So, of course, I'm not going to sell that fractal dimension is just the index that can describe all the neurodynamics on the resting state networks. But, for example, we can combine other features that we can extract from the time domain and sort it out how we can explain the neuronal dynamics underlying the resting state networks, or particular resting state networks. One thing that I want to remark is that the correlation between the frequency and the fractal dimension is more than a linear correlation, is more a quadratic correlation. So I think that integrating broad information can give more information than the two features alone. So I'm going to conclude with this take-home message, saying that fractal dimension is an innovative way for monitoring brain function and detecting abnormal occurrences based on the neural oscillation of the brain. And as Professor Rita Ari said very beautifully in her lectures, because time matters. Thank you.